Okay, welcome to this video. So last time we have already introduced to you how to deal with the parabolic curves as well as the cables carrying concentrated load. So we have actually gone through some problems on that, and then moving on to the cables carrying distributed load. This just but simple to note the lowest and the highest point of the parabola. Say for example, if we have here a parabola carrying a distributed W here, we'll just consider the lowest point and cut it along that point. Okay, so that we have this cable cut where we have a single horizontal force at the lowest point, that is H, a diagonal force T, and the vertical result from this distributed load. And if this is X, this is Wx. Now if this is point A, we just take moments at that point. We have this one. And if this is a y distance, we can now take moments. So first we have here Wx times the distance x all over 2 from A minus h times y is equal to 0. So we can summarize that h is equal to Wx squared all over 2y. So solving for y, we have this equation, y is equal to Wx squared all over 2h, which actually implies that this is a quadratic equation, because a quadratic equation only involves no constant that is paired to the right side of the equation, which contains a second degree equation, which is actually denoted by this general equation or this general equation for parabola. So in short, we can see here that we have constant that is paired, okay, to the variable, or we can interchange that to the other side of the equation, so such as this. That is why this is again, I'm saying that this is an equation of parabolas. So it is also good to understand how it was derived out of the boundary condition. So if we consider a certain element wherein we consider a certain point of this curve, there will be a certain tensile here on this tangent line, wherein the tangent line is actually having a slope referred to an angle theta with respect to the horizontal. So we note here that there will be components here where the horizontal component is actually t cosine theta and the vertical as t sine of theta. So if you perform the equilibrium equation along x, we can just say that your horizontal component is equal to t cosine theta, and upon equilibrium equation along y, we have the vertical force is equal to t times sine theta. So we further expand v. V is actually resisting the product of the distributed load times whatever the value of its distance x. Hence, we can say that Wx is equal to t sine theta. And then we note that the slope is given by dy all over dx, and it is given by the equation of tangent of the function theta. And then by these three equations, we can now derive the equation of the boundary condition of the curve. We just derive the equation by dividing equation 2 divided by equation, so this should be equation 1. So by doing that, we have t sine theta is equal to Wx divided by t cosine theta all over h, so that t is cancelled and sine all over theta would become the tangent of theta, which equates to this expression wx all over h. And we note that tangent theta here is dy all over dx, so that this is replaced by dy over dx. And then, of course, by cross multiplication, we can transfer dx to the other side of the equation and then integrate it to come up with the y. So we have this one, and then integrate both sides of the equation. We come up with this expression. First, we bring this constant out of the integral, and then the integral of x is x squared all over 2. Of course, we need to add a constant here as the constant of integration. So finally, y is equal to x squared all over 2h plus c1. So getting the value of c1, we just have to start with the point of origin, because at the point of origin there will be no slope yet. So if we're going to substitute it in the equation, we come up with the value c1 is equal to 0. So substituting c1 here, just the same, we come out with this equation x squared all over 2h, which has actually coincided with this derivation, or simply derivation, out of taking moments at a. Now with this principle, you can almost deal with any problems involving a parabolic curve carrying any load or distributed load. Just have these moments and then apply the force triangle, because we have here three forces which forms a force triangle that we can work on. How about if we do not start with the point at 0, wherein there are certain variations on the curve? Still, we can apply the basic equations 1, equation 2, and 3, but we can never conclude to this parabolic equation, since we have just derived this out of this boundary condition, wherein we start with the point of origin. So there are cases that we have given an angle or a slope already on a certain points that we also need to derive the equation for the curve. So it is not always that the equation yields to this equation. Therefore, we are going back to this equation. So let me show you an example on a unique problem wherein we need to derive the equation of the curve first before coming up with the tensile forces on the parabola or on the curve. Okay, so let us have this problem. The cable AB subjected to a uniform loading, we can see it here, 200 Newton per meter. If the weight of the cable is neglected and the slope angles at 2 points A and B are given to be 30 degrees as well as 60 degrees respectively, determine the curve that defines the cable shape and the maximum tension developed in the cable. So the problem here is we do not have the lowest point, and the lowest point here in the given has as a slope actually. So it is, we cannot base our solution to a condition where the lowest point has a zero slope. So in this case, it has a slope that is actually 30 degrees. So this time we are going to determine the curve that defines the cable, or simply the equation of the curve, and from that we can derive the maximum tension that will be developed in the cable. Just the same, we will rely to the free body diagram where there will be AX and AY here that will yield to the tension at A, and Bx and By that will also yield to the tension at B, recognizing also the result of this distributed load that will have a 3000 from the product 200 times its distance 15. Though we have this free body diagram, if we take moments at A, we do not know the y distance here. Although we know the horizontal 15 here, we cannot go away from deriving the equation of the curve here. Okay, so in my screen I have actually preserved what we have derived a while ago on the equation of the curve, that is y is equal to wx squared all over 2h plus c1. So what we'll do is to manipulate this to be able to come up with the equation. And it should be noted that this equation came from these three equations. Summation forces x, we have t cosine theta is equal to h. Summation forces y, t sine theta is equal to wx. And this is a general rule of the slope dy all over dx is equal to tangent theta. And then we note here that equation 1 came from this differential element d over dx, t cosine theta is equal to 0. And this came about by taking summation forces x considering an element of the tensile and the cable. So applying derivatives where those delta will approach 0, because when we approach 0 there will be no slope, therefore our h will be always equal to your component of horizontal of the t with respect to the horizontal, that is t cosine theta. The same true with this one. This came about by applying equilibrium equation along y, okay, and then applying derivatives where we also apply this limit. So the x approaches 0, y approaches 0, and the delta theta approaches 0. So let me also add the tensile is approaching 0. So anyway, let us not make things complicated. What is important here that if you are going to integrate this, okay, we will have this equation t cosine theta is equal to c1, and or let us just place x here, okay. So this d over dx here, cross multiply to this, so this is integrated as t cosine theta is equal to x plus c1. So anyway, we just have to substitute that at x is equal to 0, we have a constant of h. So anyway, it will go back. So what I'm trying to point out is it will just go back to this first equation. So h is constant all throughout whenever the point is. So the cosine theta, or the component cosine theta times t, is always h at any point. So anyway, moving on to the forces vertical here, t sine double theta is equal to wx. Just the same, we cross multiply dx to this, okay, and then integrate both sides, okay. So this left side of the equation remains to be t sine theta. So because that is just eliminated there. And this will be wx plus a constant of integration. So in this case, why is it that there is no constant of integration that was derived a while ago? C1 here is being eliminated because based from the condition that at x is equal to 0, our vertical component is equal to 0. Therefore, our constant would also be equal to 0. So what is the difference here? So the sense is, on this condition, or our assumption is based from the first point wherein there is no vertical slope. So remember that the lowest point does not have a vertical slope. So if it does not have a vertical slope, only h is the tensile itself, okay, at this lowest point. So that is the condition where x is equal to 0. At x is equal to 0, it is actually the starting point wherein our slope is 0, or just that h is the tensile. There will be no, okay, there will be no vertical component such as t sine of theta. That is why this is equated to 0. So in this particular problem, our first point no longer is no longer a horizontal line, okay, so it has a slope on it. Therefore, we need to include a value of c1 here, okay. There will be a constant value for c1 in this equation. So instead of using t sine theta is equal to wx plus c1 0, we'll just have to indicate here the constant c1, okay. So this equation 1 shall remain, and summation forces y is equal to 0. We'll have to add a constant because we have not started at a point where there is no slope. So this time there is a slope, so we have to add a value of c1, and c1 is a changing value, or derive from a changing value, which is this one, okay. So actually this is a constant c1, okay. So anyway, just bear in mind that if we have 2 points that has no horizontal slope in it, we need to include c1 in this equation too. So now this will be our basis. So of course we need to include here, or we need to involve this equation 3. So involving equation 3, we need to divide 2 divided by 1. So we have this equation 2 divided by equation 1. Okay, so that t is cancelled. Sine over cosine becomes tangent. And this is just remained. We replace tangent by dy over dx. And then we are going to integrate this equation. We cross multiply and place dx to the other side. And then we integrate. This becomes y. And by the way, let us include also h here. And then by distributive property, we have this one. So I have indicated here h. Since h is also a constant, it will just divide to c1 here. So let me involve h, or integrate c1 or h within c1, so we can remove this one. And by integration, we come up with double x squared over 2h plus c1x plus c2. And then by this equation, to solve for c2, at a certain point where x is equal to 0 and y is equal to 0, we can say that C2 is equal to 0 because this is 0, 0, and 0. So C2 is equal to 0. So utilizing our slope now, by the way, this y here is assuming that an x will be equal to 0. There will be no slope. So this is actually at x is equal to 0. So at x is equal to 0, we have no value for y, okay? Because this is the initial point. So let our axis be this point, okay? However, in this particular axis, there is slope equivalent to 30 degrees. So by that, we can say that at x is equal to 0, our slope is equal to tangent 30 degrees. So we are going to utilize this equation, okay, to solve for the value of C1. So dy over dx is tangent 30 degrees. H here will just be cross multiplied to that dy over dx. So what is left in your right hand equation is wx plus c1, where x is 0. So this shall now equate that c1 is equal to h tangent 30. Okay, so we can place that in our equation. So here it is. We also use the other boundary condition where at x is equal to 15. So at x is equal to 15, your slope is equal to tangent 60. So we use this equation again, applying now our new slope that is tangent 60 degrees. So we write this equation. So of course, it will have a value of tangent 60 times h times w times x, where x is equal to 15. So the w here is actually given, that is 200 Newton per meter. And then we add the value for C1, that is h tangent of 30 degrees. So as we notice, we have a single unknown h. And finally, we have the value for h, which is 2598.08 Newton. And this is the tension at this A. Actually, h is equal to 2598.08, or the horizontal. So horizontal of this one, AX and BX. And knowing the horizontal force, can now derive the tension at A and tension at B. Since both are 2598, we have the angle here, which is 60 degrees. We'll just have to derive this out of function of cosine. So we have adjacent over hypotenuse, TB. So therefore, it shall equate to 5,196 Newton. Okay, so similarly, we have another angle here. Say beta is equal to 30 degrees. You can also apply the same function. Cosine 30 degrees is equal to 2598 all over tension at A. So we have an equivalent of 3,000 Newton. Okay, so these are the answers. And for the equation of y, so the equation of y is this one. Okay, so for our convenience, you might want to consider remembering this formula. We're in. If we have a lower point, say 1 and a higher point 2, where the slope at point 1 is not 0, so you might have this formula which summarizes to this: y is equal to wx squared all over 2h plus h tangent of the slope at 1 times x. So you do not need to memorize this, because if you know this, you can already manage to solve the problem, because as we can see here, we only need y for us to move on, okay, to move on with our solution. So if we know y, by substituting the values here, then we can manage to solve the problem. Okay, so I think we also have h here, in which we could also consider equation of dy over dx, where that equation is this. So we have dy over dx is equal to, or we multiply this by h, is equal to wx plus c1 wx plus c1. Okay, and actually this shall solve everything as long as you apply the boundary conditions. Okay, so this is for the problem, and thank you for listening. So I think this is the variety of problem that is moving away from our general rule. But anyway, if you know the concept about these three equations a while ago, or the boundary equation, say we have these three boundary equation, then we will not get lost. Okay.